Hello everyone, welcome to our paper presentation. My name is Yan Mao Man. Me and Dr. Ming Li are from University of Arizona. Dr. Ryan Gerdes is with Virginia Tech. The title of our paper is GhostImage, Remote Perception Attacks Against Camera-Based Image Classification Systems. If you want to find the full version of the paper, you can Google GhostImage attack. Do not type in just ghost image. You don't want to do that. Now, in this work, we propose a type of attacks that compromise the camera in a way that its output image is misclassified by an image classifier. To make it more formal, we consider autonomous systems in our system model. Typical examples of autonomous systems include a thermostat, a self-driving car, as well as surveillance systems. In these systems, sensors are used to perceive the environment, converting analog signals like the sound, the light, and the temperatures into digital ones. Then the digital signal are then analyzed by algorithms such as image classifiers, object detectors, and sensor fusion algorithms. And these algorithms will generate decisions to the actuators that will interact with the environment with actions. In this work, in particular, we consider a type of attacks against the perception domain, where the sensor is manipulated in a way that the subsequent algorithms will make mistakes that are intended by the attacker. Now, there are many types of sensors, and they are very common in our daily life. For example, we have microphones, light sensors, radars, lidars, and cameras, and almost all of them have been studied from the perspective of security. For example, microphones have been shown that it can be compromised by light interferences. Light sensors have been shown that they are vulnerable to electromagnetic induction. Radars, lidars, they have all been studied from the perspective of security. In particular, a recent work shows that lidars can be attacked in a more sophisticated way that the attacker considers not only the sensor itself, but also the algorithms behind it. Cameras, which are the focus of this work, have also been studied before. In these existing attacks, the attacker aims to blind the camera using, for example, lasers. These attacks are essentially denial of service attacks, and they are easy to detect, and they do not consider the entire system as we do. What we want to do is to induce misperception of objects in a remote way and without blinding the camera. In our camera attacks, we are able to induce an image of a stop sign into the victim camera using a projector. More importantly, the induced stop sign image is detected by YOLO, a state-of-the-art object detector. This phenomenon is essentially what we have known as lens flare effects, or we can call it a ghost effect. Lens flare effects are very common in our daily life. For example, here is a photograph that contains multiple ghosts. We can see a ghost here, here, and here. The reason why there are ghosts is because of the imperfection of lenses, where light beams are not only refracted, but also reflected among lenses before they reach the CMOS imager. Here is a toy example. Let's consider a system with two lenses. Here is the CMOS sensor that's behind the lens, and the aperture that's in front of the lens, which controls the amount of lights coming into the camera. And typical aperture looks like this if you look at it from the left. The light beams coming from the light source bounce between the surface of the lenses before they reach the CMOS sensor. And the shape of the ghost is typically in polygons because the whole of the aperture is in polygon. Now, normally, ghosts are pieces of single color artifacts like these, but why do we have stop sign patterns in our ghosts? The reason is that projector is a special type of light source that shines light beams in different colors densely. When the other half of the light beams are in red, for instance, the resulting ghosts will have a 2x1 pattern in it. Okay, but what can we do with this phenomena? In this work, we consider two different attack objectives. First, the attacker is able to mount creation attacks where non-existent object can be created using a projector. For example, a stop sign can be created on the highway when the car is running on the highway. Secondly, the attacker can also mount alteration attacks where an existing object is modified to be classified as some other class. For example, in the surveillance scenario, we have a camera. Let's suppose we have a camera, and the camera is sitting at the front door of the house monitoring the street. If it detects a person who's getting closer, it raises an alarm. An intruder can alter his or her image into a bike, for example, so that he or she can get into the house without causing an alarm. Well, is it trivial to achieve these two attack objectives? Before we can answer this question, we need to discuss the adversary model, including the capabilities of the attacker. We assume that the attacker is able to have a copy of the victim camera. We also assume that the attacker has white box knowledge of the machine learning algorithms. We also assume that the attacker is able to track and aim the camera. These three assumptions are very common in sensor security research. And furthermore, we assume that the attacker does not have access to the output image of the camera. This brings lots of troubles to the attacker. Now, the attacker needs to predict ghosts in terms of, for example, where are they going to be in the image? How many pixels will be in it? What if the number of pixels are very small? What about colors? What about brightness? Etc., etc. These are the challenges that we have to address in order to have a practical attack. To tackle these challenges, we propose to study the channel model between the projector and the camera, as well as leveraging adversarial machine learning. More specifically, the channel model studies the channel between the projector and the camera in terms of the resolution, the distances, the colors, the randomness in the channel, etc. And we also adopt adversarial machine learning-based optimization techniques to find those attack patterns that, on one hand, maximize the attack success rate, on the other hand, obey the channel characteristics. Now let's begin with ghost pixel coordinates, or where are the ghosts going to be in the image. Here is an observation. Let's say we have an image plane. Suppose we have a light source right here, and the corresponding ghost is right there. We observe that the line LG always crosses the O, which is the center of the image. In addition, when both of them start to move, the ratio between LO and LOG is always identical at any time. Therefore, given the location of the light source, we can calculate the location of the ghost. In order to have the location of the light source in the first place, we can calculate it using homogeneous transformation with camera matrices, which essentially transforms the real-world coordinates of the light source in 3D into image coordinates, which is 2D. Now, the second challenge is about the pixel resolution. How do we know how many pixels we'll get into a ghost given the arrangement of the projector and the camera? And also, what if the situation is that we can only have very low resolution? Previously, we have this toy example. Two light beams coming from the light source in two different colors go into one ghost, so that we have a 2x1 ghost. If we further increase the projection resolution like this, now we have a 3x1 ghost. So we know that the ghost resolution is proportional to the projection resolution. Well, on the other hand, if we increase the distance between the projector and the camera, then only two light beams are able to pass through the aperture. Therefore, we end up having a 2:1 ghost again. Now we know that the ghost resolution is also proportional to the inverse of the distance between the projector and the camera. At short distances, we can just project the image of the signs. But what if in some situation we can only have low resolution patterns in the ghost? For example, based on our experimental setup, at a distance of 1 meter, we can have a 32 by 32 patterns in the ghost. However, at 5 meters, the resolution goes down to 2 by 2. And simply downsampling a stop sign image into a 2 by 2 image doesn't really work because it cannot be recognized as a stop sign by the image classifier. To address this, we incorporate adversarial machine learning into our attack, where we will formulate an optimization problem that returns low-resolution patterns that are able to be recognized by the machine learning algorithms. A typical example of adversarial examples is like this. An image of a panda is perturbed in a way that the resulting image is misclassified as a gibbon. Meanwhile, we human beings see them as exactly the same. Similarly, the attacker in our case can find an optimal 2 by 2 attack patterns that turns a stop sign into a yield sign. To find those optimal patterns, the attacker solves this optimization problem. The attacker minimizes the perturbation amount or the perturbation magnitude because he or she wants to use as little power as possible. We do not put the magnitude to be norm-bounded as a constraint because the perturbation will not be observed by a human directly. It is observed by the autonomous system without human in the loop. Meanwhile, the attacker increases the chance of deceiving the classifier by minimizing the attack loss. More importantly, the Y here is the perturbed image that is composed by our projector to camera channel model, which studies the auto exposure control, color calibration, and the randomness in the channel. In particular, when an input image is given to the projector, the digital to analog converter here in the projector converts the RGB values into lights. The lights are then amplified by this analog amplifier. The gain is controlled by this variable P sub A. D here is the distance between the projector and the camera. X here is the background of the pattern, which can be the sky, for example, or the benign traffic sign. The analog to digital converter in the camera then converts the light back to RGB values, which are used to determine the exposure of the next frame. If it's too bright in this frame, then the camera will reduce the exposure of the next frame by, for example, you reducing the size of the aperture. We need to calibrate the color because the DAC and the ADC in the projector and the camera respectively are not perfect. Finally, it comes to the evaluation. In our attack setup, a projector is placed in front of the victim camera, and we used a zoom lens that was designed for DSLR cameras to replace the factory lens of the projector in order to increase the pixel resolution at large distances. We've conducted the attack in both indoor and outdoor experiments. We've tried 3 different data sets with different network architectures. We used 3 different cameras to test the attack. We vary the projector to camera distances. There are 2 attack scenarios that are being considered. We tried self-driving cars. We also tried surveillance systems. Here is the result on traffic sign recognition. The x-axis is the distance between the projector and the camera. The y-axis is the attack success rate. The emulated result means that it is the digital evaluation considering the channel, while experimental results are collected from actual real-world experiments. We can see that as the distance increases, the overall success rate decreases. At 1 meter, we are able to achieve 100% successful creation attacks and 90% of the alteration attacks. But at 5 meters, only 25% of the alteration attacks are successful. This is because the resolution are very low at large distances, so we don't have enough degrees of freedom. We would like to argue that this is limited by our experimental setup. There are many other ways to improve the result, which is discussed in our paper. In terms of emulated attacks on other datasets, we have similar results. Note that the success rate at 5x5 resolution against the ImageNet dataset drops a lot. This is because we use the Inception v3 neural network to recognize the image from ImageNet. And Inception v3 is a 1000 class classifier. Simply having 5x5 resolution doesn't give us enough degrees of freedom. In our outdoor experiment, we placed a camera on a vehicle. The projector is on the sidewalk. The attacker is able to alter the stop sign, the real stop sign right there, into 3 other signs with very high rates. Note that at noon, the attacker was not able to achieve successful attacks because the sun is too strong compared with the projector. We would like to argue that the attacker can always acquire a more powerful projector, such as laser-based projectors, to beat the sun. We also evaluate our attack in surveillance scenarios. We assume that in the surveillance system, a camera is used to detect whether there are human-related objects in the image. Here we used a ring camera that is built for surveillance purposes. We picked several images from the ImageNet dataset that contains human-related objects, such as sunglasses. The goal of the attacker is to alter these objects into something else. We can see that the untargeted attack success rates are 100% successful. Let us briefly talk about potential defenses. First, we can make some physical modification to the system. For example, in photography, people often use lens hoods to reduce the flare effect. However, they would also significantly reduce the angle of view, therefore may not be appreciated in autonomous systems. There are also these fancy lenses called the liquid lens. Their shapes can be changed on the fly in order to alter the focal length so that people does not have to use multiple lenses to achieve variable focal length. And thus, only one lens is enough, which will largely reduces the number of ghosts. However, these lenses are still being developed and have not been widely adopted yet. We can also try to use computer vision algorithms to detect and eliminate ghosts. However, since the ghosts are transparent, it is hard to do so. Of course, we can try to enhance the robustness of the neural networks. There are many defenses against adversarial examples out there, but we would like to argue that most of these defenses are designed for small perturbations, so they would not probably work in our case. And lastly, sensor fusions may be also helpful. If the camera is compromised, just use the LiDARs instead, or radars. But please note that the attacker can always compromise all of them at the same time. but of course, the attack cost would be large. In conclusion, here is our takeaway. We are able to induce an image of a stop sign into a camera using a projector. We've developed the projector to camera channel model and adopt adversarial machine learning optimization techniques to achieve high attack success rates. Thank you all for listening. Please subscribe and hit the like button. Oh wait, this is not YouTube. Please feel free to ask any questions. Thank you.